So hello everyone, thanks for attending this presentation. So today I'm gonna do this in 3 parts. First, I'm gonna speak about compact regions, and I will present you a new primitive I added to compact regions to do very funky things. And then, in a second time, I will try to show you how to build a destination passing style API based on the primitive. And lastly, we'll see how to make the API safe using linear types. So quite a lot of things to cover. Just trying to go. Next slide. So compact regions. This is a feature introduced in GHC 8.2 that consists in blocks of contiguous memory, which can only host fully evaluated data. And the region is not traversed by the garbage collector at all. Instead, any incoming pointer from the GC heap to the region keeps the region alive. And because it is not traversed by the garbage collector, it is only freed when the last pointer disappears from the GC heap to the region. It is freed as a whole. So a region must be completely self-contained. It cannot contain any outgoing pointer from the heap to the from the region to the heap, or from the region to another region. So one first interesting use case of compact region is data serialization, of course. So when you have several programs, several Haskell programs wanting to exchange data over the network with no parsing overhead, because compact region use exactly the same memory representation as the normal GC heap, so you can exchange data without any parsing overhead. And the second one that we will be focusing on in this talk is when you have a large tree, a large data set that will stay in memory for a long time. If you move it to a compact region, you will get a lot of garbage collection saving, because instead of being traversed fully at each collection cycle, it will just not be traversed at all. So at the moment, the current API for compact regions is fairly simple, and the main function is compact add. And compact add is just a copy function. It takes something from the GC heap and puts it inside the region. And it is implemented in the Haskell runtime system in a big switch case in CMM. And basically, it has 2 modes of operation. If it encounters a thunk, it has to evaluate it beforehand, because the region can only keep fully evaluated data. And if it encounters a constructor, then it will allocate some space in the region. Then it will copy the first word of the constructors, that's to say the info table pointer, the identity card of the constructor, and that it will recursively call itself to copy the rest of the structure. And that's actually fairly limiting to have just one copy function. One example is with sharing. Compact add by default does not preserve sharing. So if you have a list in the GC heap that uses the same element several times and that element is shared, when you call copy on it, it will just be duplicated. So more memory space will be wasted. And it's even worse, of course, if you have cycles, because compact add will just hang forever and eat memory. So there is an alternative, compact add with sharing, another primitive, but it's 10 times slower, so not really satisfying. So my crazy idea is I will design a new primitive that is more simple and flexible. And I will just give a way to allocate a constructor directly into the region without making a copy from something existing already in the GC heap. So this primitive that I called compact add shallow will create a new constructor in the region. This constructor will not be complete. It will have unspecified fields. And we will only write value to the fields later on using existing memory primitives. So that could seem very radioactive, but this is not really at the moment, because as I said, the garbage collector won't go looking into the region at the moment. So as far as the user don't try to read the structure before it is fully completed, then we are kind of safe. I mean, kind of. So there is still one technical issue. How can we specify which constructor to allocate into the region? Well, that's quite tricky. We cannot just naively pass a data constructor as a parameter of a function, because it couldn't be inspected by the primitive. There is something we can do. We can lift the data constructor into a type, and then pass the type to the primitive. This is something we can do. The problem is compact add shallow is like compact add, a primitive that is run only at runtime by the Haskell runtime system. And at runtime, all type information has been erased. So we have to find a way to first transform the constructor information, that is a type at the moment, into something we can use at runtime. So for that, I need to introduce a second primitive that I called refi stg info pointer. And the info table pointer of constructor is the identity card of the constructor. Actually, it's the only things I need at runtime to allocate the proper constructor I want. So this primitive is in charge at compile time to transform the data constructor lifted as a type into its static info table pointer. And this, at runtime, will just become just a static value, a static ADDR hash that the compact add shallow primitive can use to finally allocate the constructor. So let's see how that works in action. Let's say I want to allocate a shallow left constructor. So a shallow constructor is a constructor with unspecified fields that we will only specify later. So for that, first, I use the refi stg info pointer function to get the info table pointer, and then I can just call the compact add shallow primitive that I designed in the RTS to allocate the constructor. Of course, that is still a bit unsafe. We need to specify the field's value before the user can read this. So now, second part, we'll see how we can build an API around that to make it user-friendly and usable by the user. So for that, I need two new types. First one being dest. So dest, shorthand for destination, is an opaque wrapper for a single-use pointer. And that pointer will point to the hole inside the shallow constructor. A hole is a yet unspecified field inside the constructor. So the idea is to have the destination type act as a witness of a hole inside the structure, and also as something we can consume to write a value into the hole. And then I will need a second one that I called incomplete. The role of incomplete is to act as a wrapper, an opaque wrapper, around the structure that is being built. So it has two fields, one of type A and one of type B. The field of type A will ultimately be the final structure we have built. But at the moment, it's just made of shallow constructors plugged together, and it may still contain holes. And the B side, on the other hand, is of arbitrary shape, but it must contain exactly one destination per hole remaining on the A side. And so the incomplete wrapper itself and the destinations of the B side live in the garbage collected heap, so they can be collected fastly. But the A side lives into the region and will just be the thing that will persist in memory at the end of the building. So in that slide, I will focus on how to use destination to actually build the list 1, 2, 3. So first, we use the allocprim function that I will detail on the next slide. And this function gives us a root destination. And we can consume this destination to build little by little the structure on the A side. So first, we call the fill@cons API function, passing it the destination dr. And what it will do is allocate a shallow cons cell on the A side and plug it into the hole pointing to by dr. And then we get two new destinations pointing to the new holes inside the structure on the A side. And again, we can repeat this process. And in this step and in this step, we can just add new cons cells to the structure. They are all shallow cons cells. The fields are not all specified yet. And at this point, we have 4 destinations remaining, one for each yet unspecified value, and one for the tail of the list. And using the fill_leaf API function, we can actually write value into the field. And using the fill@nil, we can write a value into the tail of the list. And at this point, we have no destination left to consume on the B side, which means the structure on the A side is complete. So in the previous slide, we focused mostly on destination. Here is the bigger picture, including the incomplete wrapper I just talked about before. So if we look at the implementation of allocprim, the most nested call is a call to alloc. And alloc actually creates a fresh incomplete wrapper. So there is just one fresh hole inside the region and a destination DR pointing to it. And incomplete wrappers are equipped with a fmap instance. And the fmap instance of incomplete lets the user access the destination of the B side, because the destination of the B side is the only thing the user can handle. And using the fmap instance of the incomplete, we can take the callback that the user supply and apply it to the DR destination. The F function is the building plan for the structure. It is exactly what I described on the previous slide. And when we apply that, if the user did the job correctly, then at the end, on the B side, we only have unit left, and on the A side, we have a full structure. So it is ready to be made readable for the user. And that's what we do using the from incomplete and unir functions. So if we focus a bit more on the two API functions I mentioned here, we have fillIf first. So fillIf just write a value into the hole pointing to by destination. It starts by copying the value we want to link to the structure into the region, and then it links it to the hole, and every destination except the one we consume that was already there is conserved, of course. But there is no new hole created by fillIf, so there is no new destination created in the process. And in fact, it is implemented using the compact add primitive, so the existing copy primitive. On the other hand, we have the fill actor primitive, which is specialized on the diagram for the cons constructor. So using this primitive, we create a new shallow constructor inside the region, plugs it into the hole pointing to by a destination, and we also return new destinations for any new hole that has been created. So we have a good toolbox to do fancy things, but it's still not safe if we can reuse a destination or forget to use a destination. So now it's time to make it safe, and one good thing for that is to use linear types. So we have three main invariants we need to enforce. First one, a destination should be single use only. We should not reuse a destination after it has been used, because we still want a write once model. We don't want to break immutability. And also, we should make sure a destination is used at least once also, because if it wasn't, there could be a hole inside the structure that is left. And second thing, the structure that is being built should not be visible by the user while it still have holes, of course, because we don't want to read unspecified memory. And finally, dest should not escape the incomplete scope, because if dest can be lost somewhere, then we cannot enforce that the structure is complete when there is no destination remaining on the B side. So if we look at the linear type implementation in Haskell, we have a linear function in Haskell only guarantees that the argument of a function will be used once if the result is consumed once. So that's not immediate, or we can force a value to be used linearly. We can only put linearity requirements on functions by default. So the usual trick to say that a resource should be used linearly is to ask the user for a callback. Instead of giving him a value and saying, you must choose it, instead of just giving a value and saying this value has linear discipline, we ask the user for a callback. And because it is a callback, it is a function arrow, and we can check the function arrow is indeed linear, and then apply ourselves the function on the argument that we want to make linear use of. So this is what the with region of my API does. It asks the user for a callback, consuming a linear token and returning something of type URA. We use UR on the return type because UR is a special constructor in Haskell that does not use the argument linearly. So because we have UR in return position, the user is forced to consume the linear token in the scope. the linear resource cannot escape the scope because it would break linearity, linearity. So with region, give the user a linear token, and then the user can use alloc with this token to create an incomplete. And because alloc is linear, then the incomplete has to be managed linearly. And then we have a fmap instance, an incomplete. And the fmap instance and incomplete is what is used to access the destinations on the B side. So because incomplete are linear and fmap is linear, then the destination have to be used linearly. And the only way for the user to get rid of an incomplete wrapper is using the from incomplete functions, the two variants. But on the B side, they ask for either unit or URC. So the user cannot remove the incomplete wrapper if there is anything linear remaining on the B side, and destination have to be used linearly, cannot be put in the UR constructor. So this is the way we infect slowly every object of the linear API. And only at the end, we can actually escape the linear scope when there is no linear resource remaining in it. So this experimental API I built give promising results on a few benchmarks. The most interesting one is parsing a large set of data, and instead of doing it directly, instead of doing it in the GC heap and maybe copying it into the region, thanks to this API, we can just build the structure directly into the region. And we get very interesting garbage collection saving and some time improvement too. The only thing is we get good improvements only on large data sets. There's still a small overhead on smaller examples. So as you've seen, with a few additions to GHC, so about 100 lines of code, I can give more flexibility to compact region usage and give rise to a good destination passing style API. So at the moment, it's still a prototype implementation. I will try to clean the code up in the coming months and follow up with a GHC proposal. But I hope it's interesting. And so I would like to thank you for your attention, and I hope you have questions.
All right, we have plenty of time for questions.
Are the benchmark results, is that against a normal Haskell implementation?
So I took parsing of S expression as a benchmark, and I wrote 3 versions. The first one where we deserialize into the GC heap. The second one where we do it in the GC heap and then copy it immediately into the region as soon as it is parsed. And the last one where we do it directly into the region. And even without using the data tree after just parsing it, it is already traversed several times by the garbage collection when it is being built in the GC heap and GC heap into region versions. So just by doing it directly into the region, we already get good improvements in garbage collection time using the direct into region version.
Yeah, it's surprising to me that the GHC heap and GHC heap into regions are so similar from form.
Yeah, I think if we wanted to see a good difference between the two, we would have to actually use the data tree for some time after parsing it. But it's kind of hard to benchmark already, and then to make some realistic use of the data tree for some time before discarding it. So at the moment, it's almost discarded as soon as it has been parsed.
Okay, thank you.
This requires basically rewriting all your code to take advantage of this. Could you imagine something where everything a particular thread allocates goes directly into a compact region?
Sorry, I didn't get the beginning.
Instead of changing all your code to use these primitives or use your interface, could you imagine something which just takes a regular Haskell expression or
Oh,
function and just directly allocates whatever it allocates, it goes into a compact region.
so you mean, can I do that without any modification of JC, basically?
No, not without modifying your code, the code that's doing the allocating. You just allocate normally, and it just goes into a compact region.
I mean, if you allocate normally a copy into a region, is what compact add does. Sorry, I'm not sure to get the question.
We can follow up later.
Yeah, sorry.
Hi. So you motivated this by saying that the default approach loses the sharing of values. So what you're doing is you put the recovery of the sharing in as a responsibility of the programmer, right? Programmer has to know which parts will be shared, retain the sharing, right?
So my main goal, to be honest, is not exactly just to recover sharing. It's just one example of a limitation we hit fairly fast when we have just one function to do everything into a region. Mm-hmm. So yeah, indeed, with my API, we are not completely solving the sharing issue because the burden is on the programmer side now. I agree.
Right, okay. And so how much would the interface be simplified by having proper linear types rather than only linear functions? Or is it just a very minor thing?
Well, I think that's a good question because we have the linear constraints paper, which basically try to improve the ergonomics of linear types. And basically, the idea of linear constraints is you determine a scope and you say linear resources must not escape the scope, but all the token passing and all the chaining between linear resources gets more immediate. Mm-hmm. So I don't think we need to really reinvent all the linear type support in JC to make it linear on values instead of on linear arrows. There are very good motivation to have just linearity on function arrows. And I think it's not really a problem as soon as we get more ergonomic things to handle that.
Okay, thanks.
Any other questions? Could you say a little bit about the context that led you to this work?
Yeah, that's a good question. So the main focus of my PhD is actually on doing destination passing style things in functional programming. And the motivating example is with destination passing style, we can basically reverse or get more flexibility on the order with which we build a data structure. For example, usually in functional programming, we have to start from the leaves of a data structure and join them together and together up to the root. And for some algorithms, this is very impractical. But using DPS, we can start from the root and slowly progress toward the leaves. We don't have to have all the leaves ready yet when we start building the structure. And this is very practical to do some imperative-like algorithms. And actually, compact regions are a very cheap way to just say to the garbage collector, don't look into what I'm doing at the moment because I don't want you to follow my pointers. They're still unsafe. So we used compact region for this at the beginning. And we say, oh, wait, maybe it's also a good way to use compact regions. So it's just 2 points of view of kind of the same two tools linked together.
All right, thank you. Let's thank the speaker.